Hi. So I'd like to talk to you about Chapter 5 on diffusion. We're not going to cover the whole chapter. We're not going to cover the non-steady state diffusion in any kind of depth, but we will cover steady state diffusion and temperature dependence of diffusion. So first of all, what is diffusion? The definition of diffusion is mass transport by atomic motion. So the atoms are moving around inside of a material. They're not still, even in a solid material, and they can hop from lattice site to lattice site. For a good video of that, I'd like to show you this one. This is carbon atoms moving at the edge of a hole in graphene and was taken in an electron microscope. So here you go. It's only about 15 seconds long. And you can see the carbon atoms over here on the edge hopping around and the motion of the atoms here on the edge of this little hole. So that's really kind of a fun thing to see. There's tons of these sorts of movies out there on the web. There's links in the PowerPoint presentation to 3 or 4 of them right there. So if you'd like to watch more of those types of images and movies taken in electron microscopes, then that's nice. And they're there for you. Now, of course, no atoms are still. Gases and liquids, you might have heard of Brownian motion. This is somewhat similar. It's not as a random walk because, of course, in a solid material, they're hopping from lattice site to lattice site, so they're not free to go just anywhere, but it is kind of the same idea. Now, in solids, there's 2 ways that diffusion can occur. You can either have a vacancy, and the atoms can hop into the vacancy, and we discussed how there's always going to be a certain amount of vacancies in a solid material. Or you can have interstitial diffusion, where you have a smaller atom moving through a material, and it's hopping in the little vacancies in between the lattice sites. And so that's the 2 different mechanisms that diffusion can occur in. So in interdiffusion, let's say that you have some sort of material and the 2 different materials meet up at some junction. And then what happens is that if it's an alloy, the atoms are going to migrate from regions of high concentration to regions of low concentration. Now, similar to what you might have learned in thermodynamics or statistical mechanics, this isn't for any profound reason, okay? It's just that things have a tendency to hop around, and even if they hop around totally randomly, what that's going to end up doing is melding them together so that it's uniform. So this is very much the law of thermodynamics, where systems tend toward disorder. Here on the left, we have this very ordered system with one type of atom on one side and one type of atom on the other, and then after some time what happens is that the atoms have diffused around until they're mixed. And that diffusion would continue if you followed it on towards the end of time until the 2 solids were totally mixed and you couldn't tell where one started and the other finished. So this is the concentration profile that you would see after some time t if you watched them migrate around. Now, it's true that also atoms hop around within their own lattice sites, as we saw in the movie, in the SEM movie that the electron microscopy movie that you just watched. You saw carbon atoms hopping around within their own lattice. However, from a macroscopic viewpoint and materials standpoint, it doesn't matter too much when they do that. I mean, really, why would you care most of the time if an atom hops in the forest? Does anyone care? So self-diffusion, maybe not covered as much in material science just because it doesn't usually matter too much. Okay, diffusion mechanisms. We watched the movie of how atoms are hopping around. Basically, in vacancy diffusion, what happens is the atoms are just moving to a vacant site. And that's vacancy diffusion. This happens when you have an alloy, for example, where the radii are similar and they follow the rules, the Rothery-Hume rules for a substitutional solid solution, that sort of thing that we covered in a previous lecture. So this is for substitutional impurity atoms. The rate at which they hop, of course, depends upon the number of vacancies. If you have more vacancies, you'll have more hopping. And then there's also an activation energy for the atom to make that hop, and it'll depend on that as well. This is a fun little simulation of interdiffusion across an interface. and you can see the vacancies and how they're hopping around, and you can see that after time the interface there starts to look more and more mixed, and you get red atoms in the blue and blue atoms in the red regions. So the rate of the diffusion depends upon the concentration, the frequency of jumping, the activation energy, and all those parameters. Now you can also have interstitial diffusion, and that's when you have the smaller atoms diffusing in a lattice of larger atoms. And they go in the little hollows in the lattice sites. So for example, a small atom like carbon moving through iron lattice, for example, would go through interstitial diffusion. And it would hop around from vacant site or hollow space to hollow space. This has a tendency to be a lot more rapid than vacancy diffusion. In other words, two things don't have to happen to get this to happen. You just have the interstitial atom and it hops to another spot that was always vacant. Whereas in vacancy diffusion, the vacancy has to be there and then the atom has to hop, and the vacancy must move around. So that's the difference. There's a little bit of addition there, which makes the process more rapid for interstitial diffusion. Now, you might be wondering why we care about this at all. And the fact is that we've been using diffusion to alter the properties of materials for quite some time, and we continue to do so. You might have heard of case hardening or surface hardening. And this is the process of hardening the surface of a metal object while allowing the metal underneath to remain soft and pliable. So what that does is it makes a thin layer of harder metal at the surface. This is really useful in steel, okay? If you have an iron with very low carbon content, then it's going to be much softer. And then you can add carbon and make it, add more carbon to the mix. And that causes the surface of it to be harder and more resistant to scratching and wearing. This was originally known as carburizing. It's still known as carburizing. But there's other forms of case hardening as well that don't involve carbon. So the one involving carbon is called carburizing. So additional carbon is infused into the case, and then the part becomes a lot more resistant to fracture and strains on the surface. So if you're into any kind of antiques, on some antique guns, you might see this sort of motley bluish purple finish, and then you know that that part has undergone carburizing. The traditional method to do this involved packing the iron in a mixture of ground bone and charcoal, or some somewhat grosser combinations of leather, hooves, salt, and urine, all of which of course contain carbon, and then putting it in a well-sealed box or a case, which is why it's called case hardening. And then the carburizing package is heated to a high temperature, but still less than the melting point of the iron, and then left there for a long period of time. And then, of course, the longer that you hold it at the high temperature, the deeper the carbon goes into the surface. Different depths of hardening might be desirable for different purposes. If you need a sharp tool, you might need deep hardening so that you can grind it and resharpen it without exposing the soft core. But things like gears or gun parts might only need a shallow hardening for wear resistance. Processes that use diffusion now are doping of semiconductors. So for example, if you want to dope silicon with phosphorus for an N-type semiconductor, then you could deposit phosphorus layers on the surface and then heat it, and then the phosphorus will diffuse into the semiconductor and make it an N-type semiconductor, actually change the electrical properties. So diffusion still gets used a lot. Okay, so how do we model diffusion? First of all, let's quantify the quantity known as flux, okay? Your textbook uses a J to indicate flux for whatever reason. The flux is going to be the moles or mass that diffuse through some cross-sectional area within a certain unit of time. And the SI units of that are either going to be moles, numbers, or kilograms per area per time. Sometimes they use centimeters squared for the area, and sometimes they use meters squared, but it will be some SI unit of area per unit time. This is measured empirically. Basically, you can make a thin film or a membrane of some known surface area and then impose some sort of concentration gradient on it so that you put more of whatever you're trying to diffuse on one side and the other, and then measure how fast this happens, moves across the membrane in that unit time. Okay, let's cover steady state diffusion. Steady state diffusion is when the diffusion is independent of time. Okay, so you're having diffusion across, for example, some thin membrane, and on the left-hand side we show a concentration 1, and then on the right-hand side we show some concentration 2. And steady state diffusion will mean that the concentration profile across that membrane will be linear. Okay, so you have some thickness, delta X, to the membrane that it's diffusing across, and then you have a linear concentration profile across the membrane. This is covered by Fick's first law of diffusion. Fick's first law of diffusion says that J is equal to minus D times the derivative of the concentration profile with respect to the spatial coordinate. Okay, so here D is the diffusion coefficient. The units of it are area per time, meters squared per second for SI units. And then dCdx, that derivative, can also be approximated for steady state diffusion cases as the delta C, the change in the concentration over the membrane, divided by the thickness of the membrane here, given as x2 minus x1. Okay? When is this valid? Okay, well, not much, I'll tell you that, but it's valid if you have a constant supply of your dopant. For example, if you have some constant pressure of gas that you're flowing through and constantly keeping the gas at that level, then that would supply you with a constant amount of dopant over time, and that would be satisfied. Or like in the example that I just showed, if you have a really thin membrane that's separating two dissimilar but basically infinite environments, so if you just have tons of your dopant available and this sort of infinite reservoir, which is very reminiscent of statistical mechanics, by the way, then that satisfies it. Also, if you look at really short time scales, what could look of course, things look linear when you only look over short time scales. So if you only look over short time scales, even something that's nonlinear can look linear for a brief period of time. All right, let's work on an example problem for this steady state diffusion. The example here is taken from your text, and it's a phosphorus doping of silicon, like for a semiconductor, as we mentioned earlier. Okay, so one way to manufacture transistors is to diffuse impurity atoms into a semiconductor material such as silicon. Let's suppose that we have a silicon wafer and it's 0.1 centimeters thick. The wafer originally contains 1 phosphorus atom for every 10 million silicon atoms, and it's treated so that there's 400 phosphorus atoms for every 10 million silicon atoms at the surface. So calculate the concentration gradient in atomic percent per centimeter and in atoms per centimeters cubed per centimeter, given that the lattice parameter of silicon, that's the lattice spacing, is 0.54307. Okay, so what is this problem asking us? Basically, it's asking us to calculate that dCdx, or the delta C delta X, for two situations. Basically, they want two sets of units on that concentration gradient. And the first set of units will be in terms of a percent, and the second will be in terms of a number of atoms. So let's do this. So here's our delta C delta X, and what we want is we want to calculate the concentration gradient over the slab of silicon from the top to the bottom. Okay, we're going to assume that the bottom is going to maintain that constant value that it originally had, the 1 phosphorus atom for every 10 million silicon atoms. Okay, we're going to assume that it stays at that value, whereas the top, that's where it's getting dosed with the phosphorus, and that's where the concentration is going to go up to 400 phosphorus atoms for every 10 million silicon atoms. So the way that we're going to calculate that is we're going to, it first asks for the units in terms of a percentage, so we'll calculate the fraction and then multiply that times 100% to get the concentrations, and then we'll divide that by the thickness. Okay, so here we go. C for the bottom is going to be 100% times 1 phosphorus atom over 10 million silicon atoms, and that gives you 1 times 10 to the minus 5%. And then for the top, you're going to have 400 phosphorus atoms divided by 10 million silicon atoms times 100%, and that gives you 4 times 10 to the minus 3%. So your concentration gradient in terms of units of percent, delta C over delta X, will be the difference in those two percentages divided by the thickness, and that gives you minus 0.00399% per centimeter for your concentration gradient. Okay? Now, I've set this up so that my concentration gradient is negative, and that's because of the way that Fick's first law is structured. Remember, the equation said that J is equal to minus D times dc dx, and so we'll set it up so that that multiplies out to become positive for J. Now, we need to switch the units so that we're dealing with a mass. It asks for the atomic percent. And then I'm giving everything. I'm giving the number percent, and then I'm giving the mass concentration gradient as well. So I'm just giving you everything. Okay, so how do we do this? How do we switch these units over? So it gave me the lattice spacing of silicon. Basically, that's our A value. That's how big one side of that cubic unit cell is. So silicon forms a diamond cubic cell, and it's got 8 atoms per cell. So the volume of a single cell would be that 0.54 nanometers and then cubed. Now I'm going to have all my units be in centimeters, so I write that as 0.54307 times 10 to the minus 7 centimeters, and then I cube it. And when I do that, I get 1.6 times 10 to the minus 22 centimeters cubed for one single cell. Now the total volume that I have is going to be how much volume is occupied by that entire thing. So if I have 10 million atoms, and I know that there's 8 atoms per cell, then I can use that to figure out the number of cells, and then I can multiply the number of cells times the volume of one cell and get my total volume. So here I have 10 million divided by 8 times 1.6 times 10 to the minus 22 centimeters cubed per cell, and that gives me 2 times 10 to the minus 16 centimeters cubed for my total volume. So now my concentration at the top is going to be 400 phosphorus atoms divided by my volume, okay, which gives me 2 times 10 to the 18th phosphorus atoms per centimeter cubed. And then for the bottom, I've got 1 phosphorus atom divided by that volume, and I get 0.005 times 10 to the 18th phosphorus atoms per centimeters cubed. So that's a number concentration per volume. And then I want to calculate my delta C, delta X. So I subtract those two concentrations, 0.005 minus 2, and then divide that by my thickness, 0.1, and I end up with minus 1.995 times 10 to the 19th phosphorus atoms per centimeters cubed per centimeter, which is the units that it asked it for in the problem. If there's other problems that ask you to convert that to a mass, then you just use the atomic weight. The atomic weight of phosphorus is 30.97 grams per mole, and I can use that to convert from a number of atoms to a mass, which I've done here. I'll leave that as an exercise for you to convert from atoms to grams. It's tough, but it's not very tough, but if you have questions, I'm happy to answer them. Okay, another example problem for you that does the full thing. There we were just calculating the concentration gradient. I'd like to also show you how to do the full Fick's first law problems. So this example problem I also took from your book. A thick-walled pipe, 3 centimeters in diameter, contains a gas, including 0.5 times 10 to the 20 nitrogen atoms per cubic centimeter on one side of a 0.001 centimeter thick iron membrane. The gas is continuously introduced to a 5 centimeter length of pipe. The gas on the other side of the membrane contains 1 times 10 to the 18th nitrogen atoms per cubic centimeter. Calculate the total number of nitrogen atoms passing through the iron membrane at 700 Celsius if the diffusion coefficient for nitrogen is 4 times 10 to the minus 7 centimeters squared per second. Okay, so let's think about all this and put this together. The first thing that I can do is I can go ahead and calculate my concentration gradient delta C, delta X, okay? So in the problem, it gave me the concentration of the nitrogen gas on either side of the pipe. And so I'll plug that in here to my delta C. So I have 1 minus 50 times 10 to the 18th atoms per centimeters cubed for my nitrogen concentration on either side of a 0.001 centimeter pipe. Okay, so when I calculate that delta C, delta X, I get minus 49 times 10 to the 21 atoms per centimeter cubed per centimeter. So that's my concentration gradient. Now, my full equation for Fick's first law is J is equal to minus D delta C over delta X. So I've already calculated delta C over delta X, and I put that into the equation. And then the problem told me that the diffusion coefficient for nitrogen, that's D, is 4 times 10 to the minus 7 centimeters squared per second. So now I put that in. And then that gives me my value of J, which is 1.96 times 10 to the 16 atoms per centimeter squared per second. Okay, but now the problem asks the total number of nitrogen atoms passing through the iron membrane at 700 C. Okay, so that's the total number passing through. So J, remember our definition of J, was 1 over the area times the amount of mass moving through in a unit time dt. So if I want just the mass moving through in a unit time, then I have to multiply J times my area to get that value. So here, J times A would give me my dm dt. Now the area that it moves through, remember this is a pipe, a cylindrical pipe, and it's moving through that outer curved surface of the pipe. So we need that area. You can imagine the nitrogen diffusing from the inside of the pipe to the outside of the pipe, moving out radially. So we need the area of that outer curved surface, and the formula for that is pi times the diameter times the length, and that would give you the area of the outer surface of the cylinder. So that gives us pi times 3 centimeters times 5 centimeters, which is 47.1 square centimeters. So then I plug that in for my area and multiply it times J, and I get 9.24 times 10 to the 17th atoms per second, which is the answer to our problem. Remember, you can always pause the video and ask me later if you get confused. Okay, so of course, we talked in another lecture about how the number of vacancies in a material goes up exponentially with temperature. And we also talked about the link between diffusion and the number of vacancies. So since the number of vacancy increases with temperature, it makes sense that there would be a temperature dependence to diffusion. The equation that relates the diffusion to the temperature relates to that diffusion coefficient D. And D that you would plug into Fick's first law, you can figure out the temperature dependence of that coefficient using this equation, D naught times e to the minus qd over RT, or qd over KT if your units are different. So if the activation energy can be given, that's qd, and that's how much energy it takes to create that vacancy to get the diffusion to happen, and that's equal to joules per mole, and sometimes it's given in kilojoules per mole, or it can be given in electron volts per atom. If you give the units in electron volts per atom, then instead of RT, where R is the gas constant, you plug in KT, where K is Boltzmann's constant. The temperature is in Kelvin, and D naught is just a little pre-exponential that's usually derived from experiment, or figured out from experiment. Okay, so here you can see from this graph the exponential dependence on the temperature that the diffusion coefficient has. Here along the top line, you can see the temperature has been plotted, the logarithm of the temperature has been plotted. And then here on the bottom, it's 1 over the temperature that's been plotted. So you can see that on this graph it forms these straight lines. So you can see here a couple of things to note. The diffusion for interstitial diffusion is greater, that diffusion coefficient is greater than for substitutional diffusion. So here it's comparing carbon moving through iron in a couple of its different forms to aluminum and aluminum, or iron through iron, or iron through iron. Okay, so basically self-diffusion. So if you look at that, then you can see that the values here for D range from 10 to the minus 20 here on the bottom of the scale to 10 to the minus 8 on the top. And you can see that the values for the diffusion coefficient are a lot lower for that interstitial diffusion of carbon and iron than they are for the substitutional diffusion of the metals. Normally less energy is required to squeeze an interstitial atom past the surrounding atoms, so of course the activation energies are lower for interstitial than for vacancy diffusion. There's a chart in your book, a table in your book, table 5.2, that lists the values of D naught that you would plug into that equation d naught e to the minus qd over RT, and also the activation energies that have been determined experimentally for these various pairs of diffusion. So here's the diffusion species on the left. That's what's diffusing. In the second column, it gives the host metal. So here you have carbon. That's what's diffusing through the iron. That's how you read the charge. You can see that for the values of carbon and iron, the values that you read off over here, 10 to the minus 10, 10 to the minus 11, 10 to the minus 12, and then you can see that goes all the way down to 10 to the minus 22 for copper and nickel. So you can see there's a huge range of values for these diffusion coefficients. All right, let me do an example problem for you on the temperature dependence of diffusion. So here, suppose that interstitial atoms are found to move from one site to another at rates of 5 times 10 to the 8th jump per second at 500 C and 8 times 10 to the 10th jumps per second at 800 C. So calculate the activation energy for the process. Okay, so here we're going to use our equation d is equal to d naught e to the minus qv over kt, and then what we're going to do is take the natural log of both sides of that equation. So we have ln of d is equal to ln of d naught minus qd over kt. Okay, so that's the equation we're going to be working with. What it gives us here are two different temperature and diffusion coefficient pairs, but it doesn't tell us what the material is, so we don't know if it's carbon and iron or what. We have no idea. So what we have is basically two equations and two unknowns. So since we have two equations and two unknowns, we can solve. So let me show you how that goes. Here we have ln of d1 equals ln of d naught minus qd over kt1, and then we have the same equation for the second pair. We're going to subtract those two equations to get rid of our unknown. So our unknown here is the d naught. We definitely don't know d naught, but that gets subtracted out when I subtract my two equations. So then I have ln of d1 minus ln of d2 equals minus qd over k times 1 over T2, 1 over T1 minus 1 over T2. So that's what we're doing there. Now I just plug in the values given to me in the problem, the 8 times 10 to the 10th, 5 times 10 to the 8th, and the two temperatures, which I have to switch over to Kelvin, 773 and 1073 Kelvin, and then I solve for QD. And when I do that, as long as I use Boltzmann's constant here, I'm going to get my units of QD in EV. So I've got the EV per Kelvin units of Boltzmann's constant, 8.62 times 10 to the minus 5 EV per Kelvin for Boltzmann's constant. And that gives me my activation energy in EV, 1.21 EV. Now to conclude, I want to say that what we've gone over, Fick's first law, is for the steady state, which gives you a linear concentration gradient. When is steady state not valid? Most of the time. Okay, most of the time steady state is not valid. If you plot the concentration with distance, which would be our concentration gradient, for most applications you're going to get a nonlinear curve. You're going to get something that looks like a decaying exponential, maybe a power law depending on your circumstances, but you're not going to get a linear value for most circumstances. Why not? Well, if you don't have an infinite source or sink of your dopant, then you're eventually going to run out, right? Like let's say that I do deposit a thin layer of phosphorus on top of a semiconductor, that I'm not introducing a constant gas doping of phosphorus, but that I just deposit a few layers and then heat it up and let it diffuse in. Well, in that case, I've definitely got a time-dependent situation on my hands because the phosphorus is going to move into the material and then I'm not going to have any more phosphorus. So that's not a steady state situation. That's where my concentration gets changing with time. Also, you will have situations where as the concentration increases, you're going to get the rate of diffusion slowing down as they intermingle and mix. So most of the time, you don't have steady state diffusion. I'm not going to go over this in this lecture. If you're interested or if you need to know it later, there's a section of the book that deals with non-steady state diffusion, which is Fick's second law. Okay? Basically, what you do is you introduce that time dependence on the concentration. So Fick's second law is a second order partial differential equation where you have the time derivative, the partial derivative with respect to time of your concentration is equal to your diffusion coefficient times the second derivative, second partial derivative with respect to the spatial coordinate of your concentration. So that's Fick's second law. And then your concentration will be a function of your position and of time. And this is, of course, valid for most of the semiconductor doping applications that people are doing now. Okay? So that concludes what I wanted to say about diffusion in Chapter 5, and let me know if you have any questions about the material.